still one more speaker, and he's going to be talking about something that makes your code that handles event sourcing easier to test, to read, and to maintain. So you might be wondering what it is. It is the Evolution developed library, which is an open source. And it allows you to build event-sourced applications in a composable way. So you will learn definitely more about it from our speaker, who is a mentor at Scala Bootcamp, and he is also a mentor at Scala Academy in Latvia that you heard about before. Our team was explaining to you how it works. So definitely, if you decide to join Evolution and get a engineering career with us, I guess you will meet Ivan, who is our next speaker. And I did ask him about the game. I forgot about the games, yeah? Well, we already know Christian loves Tibia, and Ivan told me that he's kind of a prisoner to Counter-Strike. I'm lowering my voice because it might be a secret. Anyway, we're going back to our topic. So I want you to give a big round of applause to our last but not least speaker of this conference, Ivan Petrov, our Scala developer at Evolution. Are you ready?
Not really, I need some help.
It's okay, don't worry. Big round of applause for help coming.
Yeah, I'll get my water meanwhile.
You're not the first one here with some technology issues, but as you see, we've got experts from everything here. So we also got technicians that help you out. So no problem. And I do remind you, listen closely, because after this, we're going to have the final quiz, and it's a question from each presentation. Once again, speed and correctness, or maybe just guessing. And we'll see who's going to come out with another composable gift. You got it?
I guess so.
Perfect. Okay, so the floor is yours.
Yeah, hello everyone. My name is Ivan. And today I'm gonna introduce you with another library which Evolution made. It's called Spatch, and it's some sort of a building block for event sourcing applications. So yeah, I'm a lead engineer in Evolution, also I'm a Scala developer, a lecturer and mentor for Scala bootcamps. Yeah, and I switched to Scala from Java back in 2018. Yeah, I'm still in love with it. So yeah. So what is event sourcing? Mikhail before has brought up this topic, but yeah, let's revisit it again. So in essence, it's just a software architecture pattern, yeah, where the state of application is derived from a sequence of events rather than just storing the whole state. And every change operation represented as event, and the entire history of these events is persisted somewhere. And also you can restore your current state by replaying those events in the order in which they occurred. Yeah, and Akka persistence is a model in Akka toolkit that enables building on event-sourced applications on top of the actors system. Yeah, but there is a problem. And the problem is that the API that Akka Persistent provides is not really composable. So this is an example with persistent actor, and here the logic of handling every event is very tightly coupled with an actor. And if we're gonna want to reuse some pieces of this code somewhere else in some other actors, for instance, we're gonna end up in sharing this logic through some services, through some additional entities, and or we can copy paste. Yeah, it's also an option, but yeah, it's up to you to decide how to handle this. Also, error handling here, might be a big problem because here you're mixing logic of persistent events and updating state, and maybe running some side effects along the way. So it's a big problem. And also, there is no separation of concerns here. You have an actor which have everything here. And yeah, there's another like possibility to implement this event source behavior, to implement this this approach, but it's still like lacks of composability. You have this handling logic as a monolith. If you want to reuse some validations, it's also going to be a problem. Error handling, again, you have it entangled with state transitions, and there is no like way to manage this without like choosing different approach, without rewriting it, without like going like completely different way. Yeah, and yeah, so the problem that this approach has lack of compatibility, error handling is a problem, and no separation concerns, and this is only just like the problems which are on the surface, because like actors itself, yeah, like this receive function is just partial from like any to unit, right? It's already a problem, and there are a bunch of other problems with actors. So, but akka persistent is still like a very, very good instrument to build distributed systems with event sourcing, because it has like akka sharding. Akka cluster has these cluster capabilities, and our persistent can help us with managing this state. Yeah, and what would be the solution for this problem? And as it quite often happens with Scala, the solution is in searching a suitable monad for your like problem. And there are different type of monads out there, and let's like move step by step and reach out like the one which we are looking for. So the first one which you can start from is the reader monad. And like, yeah, imagine that like you have some sort of computation that depends on some configuration, and this computation, like every piece of logic requires it, and like you need to pass it explicitly in every function again and again. Yeah, it kind of feels fine and looks fine for now, but imagine like having a bigger config and much more sophisticated logic, and you will end up in the problem. So, and the reader monad comes to help us. Yeah, it like in essence is just like an abstraction over the function from A to B, where we kind of pass our config or whatever would be some environment as an argument, and we can do whatever we want. And as you can see, it is composable. So you can put these computations in a for comprehension, and it's going to work well. And it's read well, right? So you don't have to pass like this config everywhere. Another monad that is also exists somewhere, so reader monad is obviously not enough for us, is a writer monad. And this is something that helps us kind of, yeah, so we have some computation, and we also need to store some log information or like some intermediate like pieces and accumulate them and have in the end, right? And the writer monad will pair our result with this log, which like will be like this log type should be a monoid to combine everything together. Yeah, and here how it like could look with a writer monad. Again, yeah, you see that it is composable, and we don't have to like pass this log part of our computation everywhere. We don't have to combine it manually, so we have everything out of the box. And also, like these monads usually have some helper methods, like this writer tell. You just add something on top of our log. Yeah. But this is, again, not enough for our problem. There is a state monad. And state monad like is helpful when you have computations over the state, and instead of passing the state in every function, which should like have some further computation based on this state, you can use the state monad, right? And again, it's composable, looks beautiful, and you can have a result, you can have a state there in the end. All good. So, but it's already like, sounds like what we might want to have in the end, right? We, like in event sourcing, we have events, we need to update state. Also, we can like accumulate some events. Also, we can accumulate some side effects that should be executed in the end, right? And yeah, but it all sounds that like one monad is not enough for us. And when we end up in a situation when one monad is not enough, we have monad transformers, right? So monad transformers allow us to have like behaviors of different monads in terms of one. And we have either t, option t, and of course we have writer t. So like in this particular example, you can see that like we have this option on top of a writer. So it helps us to manage like this optional effect, right? So, and also we have state t monad with option. It like serves the same purpose basically, and this is like still writer, right? So again, this number of functions which are very useful to build these computations in composable way, right? We can extract some pieces of this like computation, like and reuse it among different like blocks. So and in state t, same thing with an option, right? So if we like should fail of even number, we will fail. If no, we'll just increment. So and yeah, so solution with state t. Again, it's composable, yeah, and combines the behavior of different monads like state and option. And again, state t comes with handy methods that allows us to build this composable function. So, but is it really possible to have more than two behaviors in a monad transformer? Of course, it's possible. We have one, a huge indexed reader writer state t monad. It like extremely powerful, right? It combines like reading from environment, logging. It like have this managing state transitions. So and moreover, it is indexed, so we can track like state changes on like every step of our computation. So it's some sort of a Swiss Army knife, right, for complex workflows. Like we need to pass configuration, manage intermediate states, accumulate logs. So, for example, in casino gaming industry, right, in casino gaming domain, we can track changes of a game state, read configuration about like betting limits, log events, etc. So, everything in terms of one computation. Like the usage could look like this. Yeah. So. We can read from environment, log the environment, modify state, get the new state, and everything in one beautiful for comprehension. But this is like too powerful and too abstract. And that's the reason why evolution came up with its own like adaptation of this monad, which called patch. So it has less type parameters than the previous one. So and this monad is designed to describe changes to state as events and combine them together, as well as produce side effects. So we have a monad, we have state, event, effect, and result, right? So once you will have your computation combined, you just need to call the run method, passing some state and the sequence number. Yeah, and you will get as a result a new state, like some sort of a final state after applying this patch. You will have a sequence number, you will have a list of events which this patch has produced, and you will have effect that you have to run if you're like sure that you persisted everything, and you will have some result in the end. So let's start from the very basic example. Like we have just an event with some number, state with like some number, and we have our patch coming to our function when we're gonna call it with like empty state basically, and starting from like minimal possible sequence number. And let's log the result of it. And in order to run it, we need to provide instances of maker and change for our patch. Kinda maker is derived automatically, while for change, you need to describe how you should apply events to your state. So this is like the very basic example and the output of it. So we're starting the patch with sequence number 0, and after executing everything, we have a final state containing 15, because we were just summing up the integers side effects. We produce 2 events, right? Our sequence number is 2, our result is 42, and in the very end, we are starting our side effects, right? So, and we captured the state after applying first event. So after applying first event, we have state of 10, and after applying second event, we have state of 15. Right. Already looks composable, right? So let's implement a bit more complex example. Imagine that we have a game which has 3 phases, like bets open, bets closed, and game resolved, and some player state who is betting during bets open phase, who participates in the game if he has any bets, and who gets also resolved in the end. And in order to do this, we can bump our patch a little bit. So let's bind it to our game state and our game event, right? And as for modded, we'll use either T for managing errors in a better way. And yeah, so gonna define the maker for our game patch and gonna define the change for our game patch. So again, in order to run it, we're gonna need those instances for maker and change. We're gonna create some analytical game patches. We'll take a look on it in a minute. And we have a run patch function which just accepts our game patch. And again, we're just calling on a run and we're folding on error. And here, as our effect type in our game patch, yeah, we're gonna be using this f from unit. So it's not just unit, right? It's a real side effect, so it should be part of our part of our modded computation. Yeah, and everything can fail. We can handle errors here. So game patches. Here's the way how it could look like. So we have some trait and we have an implementation. So there are slightly more patches than these two, but let's just have a look. So for start game, what we're gonna do, we're gonna log that we received the start game call, and we're gonna lift it to our patch. Then we're gonna validate through some helper functions that also somewhere in the project that our state at this point is just the initial one. We're gonna produce event saying that it's patch event, and we're gonna emit our side effect saying that it's patch effect. And slightly more complicated logic with bets placement where we have some sort of validation, right? But since it's either T, we just have some check. lift to our patch, and we're good. And this is like very, very basic example where we have game started, 2 bets placed, 1 bet's undone, closing bets and resolving the game. So in the end, this patch produced like 6 events and emitted 6 side effects in the end, in the order where like you can see, right? If we want to fail, we can close bets and then try to place bet, right? The whole patch will fail. So in this situation, we have no events produced, right? So we have no side effects, right? All right, let's make our example a bit more complicated, adding just one simple piece of scheduling transition automatically. So, and also, like, this is a not real world scenario, right? Where we have just like some functions calling the whole sequence of our like state transition at once. It should be like some shared mutable state, either it's akka or like whatever. But for simplicity, let's go with ref and have this transition, right? So in order to achieve this transition, we're gonna extract our like patch runner into a separate like entity. We are doing the same thing here. We are running a patch, applying our like state taken from like our like ref, but here it's a serial ref. The only difference that it has semaphore and allows to update state passing effect inside. So it's not just like update from A to B, but it's update like F A to B, right? A to F from B, basically. So it allows to make it effectful, and it's just the same thing which we've seen before, right? But it's just a separate entity which can which has the state and makes this update taking state from the reference and then updating it in the end. And we have this internal state. So our game patches now look mostly the same, but with some like changes, right? We have this new transition effect, and our game patches now accept this patch runner. And the beauty of this is that we can execute patches there, right? We can just call the patch runner, and as a result, it returns us like F from unit. It's a side effect, and we can run it. But let's make a step back, and you will notice also that now our effects kind of executed in a separate fiber. We're forking this execution, because if we want to do this particular sleep will just sleep the whole game, right? But we don't need this. We need to run this in the background. And yeah, this is a game example here where we just starting the game, placing some bets with some intervals, undoing bets, and we're trying to place bet once bets should be closed already. So we expect to see some rejections, and like eventually we just resolve game, right? So we see that like we have started the game, we scheduled like our close bets there. Eventually we are closing the bets because this patch is getting executed after those 5 seconds. And yeah, we are failing this place bet because we have invalid game state. Bets are closed already, we cannot place any more bets. Yeah, so, but these are very, very like simple examples, but they still show the power of this patch monad and that it's really composable. But yeah, let's check like the last example of a more complex game flow where we also have bets processing. And bets processing complicates our game flow because we should like process bets in some like time, and if bets didn't manage to process on time, we should reject them. If bets are processed on time, we should accept them, or we should reject them if they like were processed when it's already like too late. And this already sounds like the logic will be, which well, like we'll have much more lines of code, right? So we can just start packing our patches into separate entities, right? And just having this aggregation of game patches for usage. But they will basically call underlying patches. And it's gonna look like this. So on top of our game patches, we're gonna have constructors for our particular patches, and we can structure the code in the way we like, right? And basically, we can decide how to run these effects, how to run everything inside of this. Maybe some patches will be very, very simple, so they won't require these like broad conflict boundaries type classes. Like monad would be enough for most of them, probably. We're gonna need like maker and change, but yeah, like monad will be enough, no temporal or whatever. But here we're scaling transition, and yeah, for closing bets, we have a very kind of sophisticated logic in here. It's nearly the same as for starting games already. We've seen it before, so we're starting this scheduling state transition to finish bets processing. And we are processing bets as well here. But in order, like, again, not to have these effects waiting each other, we are like, can start this state transition right here, not waiting for a patch to run, right? And in process bets, we are calling our transaction service, creating this transaction, and like after bets closed, right? We've seen that player has bets. Now he's in bets processing state instead of idle, since he has bets. And for him, we're running this effect. If player is not in this state, we're doing nothing. It's just empty effect. But if it is, then we are running effects. And as a result, right here, we can decide how to branch further, right? So we can handle error. We can check what state at this moment, because like transaction creation took some time. Maybe we are like already late or no, but if it's just an error, we can check if we're waiting for bets processing and we still need to produce bet rejection event to reject this bet, or we are doing nothing because it was rejected like when we were finishing this bet processing. And if it is a success, right, we're still checking if it's still bets processing and if we can accept it. So, and if we can, we accept it. And also producing this effect. So if we didn't manage to accept, we need to cancel transaction. So it was created, but for the game, it's already too late. We reject it. If it's fine, we accept it. Yeah, so this is example. We just like starting in the game, waiting for some time, placing a bet, and sleeping till it's like fully finished and resolving this with some result. And in a happy path scenario, we've got our bets accepted before we finished like bets processing, and everything is good. While if we were waiting for too long for these like wallet operations, we got a rejection before bets processing is finished. So this logic is part of like finishing bets processing. Yeah, and as a result, our bet already was rejected, so we are canceling transaction. Yeah, this is example with a ref, with a simple state which is stored in the memory. But in the real world, you need to integrate with something, and Evolution has another library, which is on GitHub, this Akka effect, and it has this 7-source model, which is like supposed to provide you a purely functional way of running this persistence stuff. So it's a wrapper around Akka in the end. Yeah, and this like it has like some entities like engine, and once you define the engine, you can have your like patch engine on top of it. So it's still the same, right? So you have your state, you have your sequence number, and you just apply it on patch, and then you decide how to like what to do in case if it succeed, and if it's failed. So main takeaways. Like the patch is a building block for open source application, which has this integration with Akka through this Akka effect open source module. It's composable and easy to test because you abstract over effect. You can test this with ID monad. You can test this with try if you have monad throw, or you can split like your complex patches into smaller ones. You can test it separately, right? And you can handle errors pretty much on every stage, because like if you're gonna use either T as your effect channel, right? And yeah, it helps a lot with separation of concerns because you can split your code in smaller parts. You can do validation like in one place. You can have your side effects in a different place. Yeah, and the hints like just use it with either T, right? You can use like your own ADT for error channel of this either T, because string like shown is this in this example is just like, for example, like just have your own ADT. Also, your effect channel might like also be an ADT indicating whether it should be forked or no, because if you like decide to fork every effect, maybe it's not like what you're looking for, or if you decide not to forking, then you will be blocking your like actor and computations. So yeah, it can be like join of or fork like ADT. Yeah, and don't hesitate splitting into smaller ones your big patches. Yeah, thank you. You can find all the libraries on Evolution GitHub.
Thanks a lot, Ivan. Is there any question that you want to? There is a question, so let's use that. Why not? We got some time.
Nice presentation.
Thank you.
Actually, I work with Ivan, and by virtue of working a little bit different domain, I never touched this part, so it was like new for me as well. So I want to reformulate like main idea, and please tell me if I'm right or wrong. So the patch, each individual patch value encodes a state transition, and it's composable by virtue of like you can combine simple state transition into complex state transitions, which consist of other state transitions.
Easily, yes.
And it's a monad because the state transitions for event sourced entity are sequential. So one state transition begets another.
Exactly. They are taking this idea from index reader writer state monad. So at every moment of this computation, you can ask patch for a state, and it will return your state in current moment. So you can emit event, and you will call patch for a state, and you will get state with applied event. And if like event application will fail, you'll end up with an error already. But what's cool that like events are not persisted at this moment, right? So it's just a computation somewhere in like in Scala, and only when you persisted all the like if your patch succeeded, you persisted all the events, and you can write your side effects after that, right? So yeah, you can make very complex patches, but yeah, just probably avoid using like this avoid doing this, like building very complex like transitions, but it's possible. Yeah, like the example with transaction processing. This is like if you would think of it in like. If you think of it in a classical actors approach, you will end up with sending to yourself these commands to accept bet, reject bet, and you will process them like somewhere like separately, and you will look for this logic across your project. But here you have a patch You're closing the bets, you're placing bets, and you see how those bets are getting processed. And you, like, already there know what state it is, because it's patch, but in a different moment of time, because it's like patch inside of effect. So, but in order to achieve this, you need to have some sort of a patch runner in your context all the time. So patches can like run patches inside, turning them into side effects.
Thank you. Thank you.
Okay. Any other question, comment we got there? So for sure we got a round of applause for our last but not least speaker. Thank you very much, Ivan.